Hi. So the goal of this video is to do another example of a Fourier transform. And in my previous videos, we looked at the Fourier transform of the dirac-delta function and also of a simple sinusoid. Now what we want to look at is the Fourier transform of a pulse, where a pulse is some sort of graph that is zero for most of the time, but then we have it spike up and become flat and constant for another point in time. So it's kind of like a square wave, except we're not seeing a full period of some negatives and then some positives. We're just seeing this constant value of 1 that is on for a small amount of time, and then it turns off. That's what we call a pulse. And the reason this is important is that when it comes to filtering, this may be useful in determining how we're filtering things. Additionally, it is useful for the concept of windowing, which is a technique used to minimize spectral leakage. In class, at least this semester in the spring of 2025, we probably won't be able to get to why this pulse is important for filtering and windowing, but I hope in future semesters we do. But I wanted to introduce it because the outcome of it is important. So with our definition of the Fourier transform, which we've learned is the integral from negative infinity to infinity of the function times e to the minus j omega t. And we integrate that with respect to time to ultimately find out what our Fourier transform is, x of omega. So what's interesting, though, is that x of t is 0 for all time, basically, except in between 0 and 2. Which means that our integral now can become the integral from 0 to 2 instead of negative infinity to infinity. And if we compare, this x of t is going to be 1 inside of that range of times between 0 and 2. So it's going to be 1 times e to the minus j omega t dt. And we learned in a previous video that if we integrate the complex exponential, we would get the dirac-delta function. But that is only true if the bounds are between negative infinity and infinity. In this case, it's between 0 and 2. So this is not equal to the dirac-delta function at t, or dirac-delta function of omega, rather, in this case. That wouldn't be true because the bounds are not negative infinity to infinity. Instead, we can actually integrate this by hand like we normally would. So if we integrate this, this is just an exponential function. We can go ahead and do a u substitution type of thing to ultimately get negative 1 over j omega e to the minus j omega t. As a check, if we take the derivative, the negative j omega will come down, cancel the negative sign, the j omegas go away to give us 1. That gives us back the original function. And we will plug in our bounds between 0 and 2. And if we do this, we're plugging in these numbers here in for t because that's what we integrated with respect to. We wouldn't plug them in for omega. We plug them into the variable that we're integrating with respect to. So that 2 is going to be plugged in for t. We get negative 1 over j omega e to the minus j omega with a 2 minus e to the minus j omega with a 0. This is e to the 0, which is 1. So this is negative 1 over j omega e to the minus j omega 2 minus 1. And if I wanted to, just to get rid of the negative sign in the front, I can change the orders of these to ultimately get 1 over j omega 1 minus e to the minus j omega 2. And this is my Fourier transform of this. Now, this doesn't really give us a lot of insight into what's happening. We want to try to reduce this further so that we can get a better feel for what's going on. So what we want to do is simplify further. And to do this, we will use Euler's identity, or Euler's law. equation. Which says that e to the j theta is cosine of theta plus j sine theta. So in this example, if I look at this e to the minus j omega 2, this would be the same thing as cosine of negative 2 omega, because if you keep in mind this j here matches this j, that means that the theta is negative 2 omega plus j sine of negative 2 omega. Go ahead and erase these reds because they're not deleted. As I mentioned in another video, based on the idea of the unit circle, we know that the cosine of a negative angle is the same as the cosine of the original angle, while the sine of that angle changes signs, S-I-G-N. So this is the same as this, cosine of 2 omega minus j sine of 2 omega. We can plug that in now into our x of omega. If we look at that, this is going to be 1 over j omega 1 minus, and then I'll include in parentheses, cosine of 2 omega minus j sine of 2 omega. And I'll distribute that negative. It'll be 1 minus cosine of 2 omega plus j sine of 2 omega. All I did there was distribute the negative sign to the blue parentheses. I'm going to go ahead and also distribute the 1 over j omega. I'm going to include the 1 with the cosine of 2 omega term. We'll see why. If I do j sine of 2 omega over j omega, the j's will cancel. So I'll end up with sine of 2 omega over omega. Okay, this looks like a thing, I guess, but I'm not at the goal I want to get at yet. We're going to use a couple trig identities here. First off, and I never memorize these, I always forget them. It's 1 minus cosine of 2 omega is the same as 2 sine squared of omega. Let's move this down a bit. Sorry. Let's get some more room. Stop it. Okay. I hope we see it's apparent. I'm going to plug that in up here. And I also know that sine of 2 omega is 2 sine of omega cosine of omega. Those are the trig identities I want to use, because what I can do now is say that x of omega, this numerator here, I will plug in 2 sine squared of omega divided by j omega. And then similarly, the sine of 2 omega, I will plug in this trig identity for 2 sine omega cosine of omega divided by omega. And I'm going to take some stuff out of this. I'm going to factor out, what do we have in common? We have a sine omega in each term. Choose a different color, choose yellow. I have a sine omega in each term. I have a 2 in each term, and I have an omega in each term. So let's factor all that out. 2, I'm going to do sine squared. I'm going to do 2 sine of omega over omega. And what I'm left with is sine of omega over j plus cosine of omega. If I keep going, I can rationalize the j If I try to bring the j to the numerator, that implies that I'm multiplying by j over j, which introduces a -1. So it becomes minus j sine of omega plus cosine of omega. And what is this? This is cosine omega minus j sine omega. That's the same order. That is Euler. This is the same as e to the minus j omega because of this minus sign. That has to be a minus. So that whole term with the sine omega and cosine omega will reduce to just the exponential. X of omega is 2 sine of omega over omega times e to the minus j omega. And this is the Fourier transform of the pulse. Now, you might be wondering, why did I want to go to this expression? I mean, I had totally valid expressions here and any step along the way. The reason why is because if we were to go ahead and plot this, we would see that it's dependent on this expression here, sine of omega over omega. When I say plotted, I mean if we plotted the magnitude of this, this just ends up being 2 sine of omega over omega. That sine of omega over omega is commonly used, or it commonly appears in signal processing, and it has its own fancy name. This is what we call the sinc function. Oops. Sinc of omega. And the sinc function has this really interesting shape where we end up, I'm going to try to plot it, where we end up with this situation where we have these little tiny lobes that are symmetric. Let's see if I can try to make it symmetric. That's supposed to be symmetric, where on the x-axis is omega and on the y-axis is the magnitude of the Fourier transform. And we multiply by a factor of 2 because that 2 is here. But in general, this is the shape of the sinc function. And I just want you to be familiar with that concept, or if you see this graph, which has all these lobes, these little mountains that are spreading out, that is related to the sinc function. And I'm hoping this semester we'll be able to talk about why this would be important. In future semesters, I will. But this is what the Fourier transform magnitude looks like for a pulse. I hope this video was helpful. If you have any questions, please let me know. Okay, thanks. Bye.